Okay, I think we can start. So welcome everyone, and today we are happy to have Christian Ferko, and he's going to talk about duality-invariant nonlinear electrodynamics stress tensor flows. So please start.
Great, thank you very much for the invitation and the opportunity to speak. I'd like to tell you about some interesting work that I did with a set of very good collaborators. So Gabriele Tartaglino-Mazzucchelli and Sergei Kuzenko, who I think I just saw maybe join in the audience, as well as Gabriele's PhD student, Liam Smith. And the big picture idea, or the motivation, I guess, of what we've been thinking about is broadly how one can deform a theory or a physical system in a way that preserves some desirable property. So this is a very common theme, as I'm sure you know in physics, that one often would like to deform a system in a way that preserves something like integrability or supersymmetry or some other property that we like about the system. And in studying the collection of deformations that one can do that preserve such a property, we often learn a great deal. So this is usually a useful strategy to adopt. And in this context, or in this particular project, the property which we'll seek to preserve, or the useful feature of a theory which we would like to keep under deformations, is electric magnetic duality invariance. So the schematic picture is, we'll think about some seed theory, which is self-dual in the sense that it's mapped to itself under some duality transformation. And we'll deform by some operator, which I call math cal O, to some deformed theory, which is also self-dual, which is mapped to itself under duality. Now, there's many reasons to be interested in self-dual electrodynamics. One of them is that there's some connections between self-duality in electrodynamics and spontaneously broken supersymmetry, which is also related to deformations by the stress tensor, which I'll talk about. But since this talk isn't really about supersymmetry, I'd like to start by giving a sort of broader perspective and making some very basic statements about duality to contextualize this in terms of more big picture motivation. So broadly speaking, you might say, well, duality is interesting because it appears in many, many cases in physics. There's many familiar examples of dualities that we hear about all of the time. They include things like holographic duality, which we often hear about, relating gravity and gauge theory or conformal field theories. There's other examples like particle vortex dualities that maybe relate, in this example, two different three-dimensional gauge theories. And other examples of dualities, which I put in this second category, type B, such as T-duality in string theory, that relates a theory with one value of a parameter, here the parameter is the size of some circle R, to the same theory, but with a different value of the parameter. The circle is of size alpha prime over R in the dual frame. Another example in this class is these strong-weak dualities, like an S-duality in type 2B string theory, or this Montan and Olive duality. And these also relate a theory at some value of a coupling, often it's a complex parameter tau, to the same theory at a different value, say the S-dual minus 1 over tau of the same coupling. So this breaking into two categories is somewhat artificial, but the difference I'd like to emphasize is that although in both cases, the examples of duality that we're familiar with involve two seemingly different descriptions of the same physical system, that's what it means to be a duality, there are some cases where the duality relates theories with different fundamental degrees of freedom or different Lagrangians. For instance, in the holographic case, the gravity Lagrangian can be the Einstein-Hilbert action or a string theory in the bulk, and there's a different theory with different degrees of freedom on the boundary. Whereas in type B, these second type of dualities, the fundamental degrees of freedom in the theory are the same, but what has changed on either side of duality is simply the values of certain coupling constants. So I'm going to focus on this second type, this type B of dualities. And this is what I've just said, that either in type A, one can have different degrees of freedom, or in type B, the same degrees of freedom, but with different values of coupling constants, since those are part of the data that defines the theory. And the main example that we'll be interested in this talk is this electric magnetic duality, which in the most basic or the most perhaps familiar example of this duality is a relationship between solutions to the equations of motion for the Maxwell theory with both electric and magnetic sources. So in the presence of both an electric current J mu E and a magnetic current J mu M, the equations of motion for the Maxwell theory look like this. We relate the divergences of the field strength and its dual to these currents. And here, everywhere, I use this tilde for the Hodge dual of a form. And these equations are invariant under replacements. So one can replace the field strength with its dual and the dual with minus the field strength, and at the same time exchange the electric and magnetic currents. So this is kind of the oldest presentation of electric-magnetic duality, is this sort of simultaneous exchange of field strength and dual and the two types of currents. Now, the reason I say that this is type B, recall, was a duality where the degrees of freedom stay the same, but certain couplings change. The reason I'd like to think of this as type B is because when one has a collection of sources, electric and magnetic sources, those are characterized by certain coupling constants, which we call the charges, say the electric and magnetic charges. And those are part of the data that defines the theory. Those are coupling constants within the theory that tell you how the electric and magnetic charges interact with the field strength, say. And because this duality exchanges those couplings in the generic form that I've shown on the previous slide, this modifies the data of the theory and is therefore in the second class of dualities that I've described. But there's a special case. Although I've emphasized a generic duality relates to different theories, there's a special case, which is the vacuum, where there is no coupling data to change. So there's no electric or magnetic charges to worry about because we're studying the vacuum. And in this special case, the duality relates two instances of the same theory, since there's no data to change. So this, for instance, takes one solution of the equations of motion to another by exchanging, in this case, when both of the right-hand sides are zero, we can think of this as exchanging the equations of motion and the Bianchi identity for the field strength. So we say that this theory is duality invariant because it's mapped to itself under this transformation. So as an analogy, in the string theory case, when we spoke about T-duality as an example a moment ago, you can think of this as like going to the self-dual radius. So if the radius of the circle is root alpha prime, and one performs this transformation where the radius is mapped to alpha prime divided by the radius, then you can see that this maps the radius root alpha prime back to itself. So this is another example of a self-dual case, some theory. So this is interesting because in these cases where one has self-duality, this is not a relationship between two different theories, but a map from a theory to itself. And we can therefore think of this as a form of enhanced symmetry. So the perspective I'd like to take is that self-duality is an additional constraint or additional condition you can impose upon a theory, much like supersymmetry or integrability, where there's some enhanced symmetry. And then one can study how one can deform the theory in a way that preserves this enhanced symmetry. That's the big picture motivation. So from now on, let's restrict to this sort of special case that I just described, the source-free case, where there's no currents. And hearing what I've just said, you might reasonably object and say, the Maxwell theory is very simple. It's a free theory. So, of course, a free theory can have all sorts of enhanced symmetries, because free theories are very special. So it's natural to ask, can you find some other theory of electrodynamics besides Maxwell, one which is nonlinear, that has some kinds of interactions, but which still enjoys this enhanced symmetry, this duality invariance? And to do that, we should first characterize what we mean by duality invariance in this more general setting. So this is the sort of definition I'll use, that given some other Lagrangian that need not be Maxwell, if there's a variation, a duality rotation by some, say, angle theta, I'd like to think of this as a U1 rotation, under which the field strength is mapped into this object G, which is related to the dual of the derivative of the Lagrangian with respect to the field strength F. And if the equations of motion that arise from some theory, some Lagrangian, are invariant under this rotation, we will say that that's a duality invariant or self-dual theory of electrodynamics. And one of the early studies of this condition was this 81 paper by Gaillard and Zumino. And the reason for this this definition, or why one should mix the field strength into G, is because we'd like our generalized notion of this duality invariance to be one which relates or interchanges the equations of motion for a theory and the Bianchi identity. And the equations of motion will be related to the divergence of this quantity, this derivative of a Lagrangian with respect to the field strength. So this is why G naturally appears in the generalization. Okay, so this is the definition. There are other interacting theories that enjoy this duality invariance. Another important example is this Born-Infeld theory of electrodynamics, which appears in string theory, where it describes the world volume gauge theory on a D-brane. So I'll say more about that in a moment. So that's an example of a duality invariant theory. We'll also need to use a notion of a duality invariant function, and that is defined by the property that within a given theory, defined by some Lagrangian L, if some function O that depends on the field strength is invariant under this duality rotation, then we say that O is a duality invariant function. And the reason I introduce these two different notions is because the Lagrangian itself need not be a duality invariant function for the theory to be duality invariant. It's only necessary that the equations of motion are invariant under duality rotations. Even the free Maxwell theory, in even the free Maxwell theory, the Lagrangian itself is not duality invariant. It's just the equations of motion. So that's why I have these two notions. Okay. So I mentioned the Born-Infeld theory. So I've written here the Lagrangian for the Born-Infeld theory, which has a parameter alpha. And I'll mention a sort of mysterious looking fact, which I first learned about years ago in the context of these so-called TT bar deformations, which started to motivate my interest in this area and some of this work. And the strange fact is that if one takes the Lagrangian for this Born-Infeld theory and computes its Hilbert stress tensor, or its energy momentum tensor, by varying the metric, one can show that this Lagrangian obeys a certain differential equation. So if you take the derivative of this Lagrangian with respect to this parameter that I've called alpha squared, that derivative can be written as a particular bilinear or some quadratic combination of energy momentum tensors, subject to an initial condition that as alpha goes to 0, this reduces to the free Maxwell theory. And in the string theory setting, this alpha is related to the brane tension. So the picture is that one can imagine a sort of curve or a line in the space of theories, which starts from a point which is the Maxwell theory, and then the tangent vector to this curve, as you move away from the initial point, is some combination built from the energy momentum tensor. So this generates a sort of curve in the space of theories of nonlinear electrodynamics, but with the property that all of the theories along that curve, which are here the Born-Infeld theory at different values of alpha, are all duality invariant. So we get a duality invariant family of theories from this differential equation. So this seemed kind of mysterious to me when I first saw it. So part of the goal of the paper that I'm going to describe is to address the question, is there a more general relationship between these duality invariant theories and such differential equations involving the stress tensor? Is there something deeper? And the answer is yes, as we'll see. And you can understand this deeper relationship either directly by studying the Lagrangian without any additional tricks, or one can also use an auxiliary field formulation that was introduced by Ivanov and Zupnik some 20 years ago, which makes some aspects of this correspondence more transparent. So that's the sort of framing or big picture motivation. That was the introduction. In the rest of the talk, I'd like to give some more details about this correspondence. In part 2, I'll explain some sort of simple but I think interesting theorems about these duality invariant theories using a direct analysis of the Lagrangian. In the next part, I'll speak about this auxiliary field formulation that I mentioned, and then summarize with some future directions. I should stop here and see if there's questions or comments in the first part, the introductory part of the talk.
Well, I have a question. So does that mean in some sense, like the fact that, well, somehow you have this differential equation for your theory, which like the initial data is the free theory. Yeah. Yeah, where it was d alpha of L equals, yeah. Well, I'm just wondering whether it means that the deformed theory is some sort of a change of variables from in the free theory or something like that. Because the deformed theory is constructed solely in terms of ingredients of the free theory, in a sense, right? And T, in some sense, generates coordinate transformations or something like that.
Yes, that's a very good question. So in other contexts where theories obey flow equations of this form, for instance, in 2 dimensions, what you said is true in the sense that one can realize the deformed theory as some particular, I hesitate to say diffeomorphism, because one can perform a change of variables where the coordinates themselves depend on the fields. So a field-dependent change of coordinates, or a stress tensor-dependent change of coordinates, which is a strange thing to do. But this has been studied in the 2-dimensional setting, and there it is true that deformations driven by the stress tensor are equivalent to these field-dependent changes of coordinates. So one can do a precise mapping between, say, solutions of the undeformed equations of motion to solutions of the deformed equations of motion by doing such a transformation. I don't know yet whether the same sort of interpretation can be given to these higher dimensional, here 4-dimensional flows, but it seems very likely for the reasons that you said, that roughly that the stress tensor is the Nerta current for, say, spatial translations, so it should somehow be related to spacetime symmetries, and perhaps doing one of these strange field-dependent changes of coordinates would also generate the Born-Infeld theory. That's an interesting future direction.
Thank you.
Sorry, I have two small questions. So first question, I mean, this duality, is it discrete symmetry or is it like SP2R, something like that?
Oh, good. So the first example I showed was a discrete duality where one is just doing replacements. I guess this is like a discrete Z4 duality, but this can be elevated to a continuous version. So I without explaining, shifted to the continuous version. So this is now a U1 duality where one is doing a sort of continuous rotation. But I'll always be interested in the continuous version of these duality transformations in the rest of the talk.
Okay, thanks. And the second question, in this deformation with the stress tensors, there is some relative coefficient between the 2 terms. Is it important, or you can have it arbitrary?
Yes, this one turns out to be important. So one only recovers the Born-Infeld theory with this particular choice of coefficients between the two invariants. So you could ask, I mean, what happens if you do some other general deformation by different, change the coefficients or use some different function of the stress tensor. So if you do that, you will still find some duality-invariant theory by solving the differential equation, but it will no longer be the Born-Infeld theory. It will be something else. So this one is just to recover Born-Infeld. That's right.
Yeah, I have a question. So if you just consider some brane, whatever, not 4-dimensional, but any dimensional, brane in static gauge, so generalizing Nambu or this Born-Infeld, that equation will be still true, right? Leaving aside duality, just this one, yeah. Is that true or not?
No, I think, sorry, I think this equation will only work for the 4-dimensional Born-Infelds. You can do, so we've also studied the 3-dimensional Born-Infeld.
No, but in 2 dimensions. I'm not talking about Born-Infeld, just scalar theory, brane action.
Oh, just the transverse scalars like
Nambu. Yes, like Nambu. It's definitely true in 2 dimensions, and I think it is true in 4 dimensions. So my question is whether this is true in any dimension. Probably true. It's true in any dimension.
Good. So we looked at this. If you have one transverse scalar, so if you have this Nambu type action with one transverse scalar, you can write a flow equation of this form with dimension-dependent coefficients, and the theory will satisfy that differential equation in any number of dimensions.
Okay.
But if you have multiple transverse scalars, it does not satisfy the same differential equation.
Okay. Okay. All right. Thank you.
Very good. Any other questions? Okay.
Just a quick question about so there are two invariants basically, the t-squared and the trace of t-squared, right?
Yes, that's right.
So you can have arbitrary function of these two invariants. Is
Yes.
that true? Would that mean that you can generate a family of duality-invariant theories parameterized by a function of two variables?
Yes, very good. I'll explain that more in a moment, but indeed, so it's since the stress tensor for a general abelian gauge theory in 4 dimensions has two independent quantities, the trace of t squared and the trace of t, it does seem like one should have a function of two variables worth of freedom in performing these deformations for a 4-dimensional theory of electrodynamics. But it turns out that when you impose self-duality, there is a functional relation between these two invariants of the stress tensor. The trace of t squared and the trace of t become functionally related in a self-dual theory. So this cuts down the amount of freedom you have in performing one of these deformations from a function of two variables down to a function of one real variable. And that turns out to be exactly the same amount of freedom you need to parameterize one of these duality-invariant theories of electrodynamics. You have one real function's worth, or one function of a real variable's worth of freedom.
And why can't you have trace t cubed, let's say?
Oh, good. Yes. So the reason, one way to think about it is that in the field strength itself, okay, let me point at let me use this footnote here before I go to this, but the field strength itself has two independent Lorentz invariant degrees of freedom in it. The field strength F mu nu you can think of as, say, a antisymmetric matrix, which has two pieces of data, say lambda 1 and lambda 2, if you like, that are built into it. And since the stress tensor, you can show the stress tensor for a general theory of electrodynamics is based, it's built out of some function times, say, the identity, 4x4 identity matrix, plus some function times f squared, plus some function times f to the fourth, roughly. You can show that the stress tensor for any abelian gauge theory in 4 dimensions actually only has two pieces of Lorentz invariant data. So the trace of t cubed is actually always related to the trace of t squared and the trace of t for the stress tensor of any 4D gauge theory. That's just a linear algebra fact. But if it were not a gauge theory, if it were some other generic theory, then I agree the stress tensor in 4 dimensions would naively have 4 pieces of data, trace of t, t squared, t cubed, and t fourth, and then it would stop. But it's special for gauge theories that there's actually only 2 instead of 4 pieces of Lorentz invariant data. Very good questions. Any other questions or comments? Okay, well, if there's nothing else, I'll go on and show you some of the theorems. Very simple theorems, actually. So the proofs, I think, are delightfully simple for some of these facts. So let's start by describing the space of theories that we'd like to consider. I'm going to ignore any theories that depend on higher derivative terms. So I'll not consider any derivatives like d rho f mu nu, but I will consider a Lagrangian, a general Lagrangian that depends on a single field strength f mu nu in any way. So any Lorentz invariant combination of the field strength f, but not its derivatives. So as we were saying, a general Lorentz scalar built from a 2 form like f mu nu in 4 dimensions has 2 pieces of Lorentz invariant data. And one can choose to parameterize these in a fairly standard form in terms of these variables s and p. So s is the sort of Maxwell term in the Lagrangian, and p is what would have been, say, the term associated with a theta angle, which is usually a total derivative if it's just added as a linear term in the action. But one can have a general function of these two invariants, S and P. And here F tilde is the dual, as before. So one can translate this duality invariance condition that I showed you in the introduction, that a theory is invariant, or the equations of motion are invariant under these duality rotations. One can translate this to a statement about derivatives of the Lagrangian with respect to these S and P parameters. And the condition one finds after doing this translation is this. So the theory or the equations of motion defined by a general Lagrangian depending on S and P is duality invariant if the Lagrangian satisfies this differential equation. Now, as a side comment, this differential equation by a change of variables can be brought to this other form, this so-called Courant-Hilbert equation, which has been well studied, but that's sort of a side comment. I'll work primarily with this form of the differential equation rather than this different form. Okay, so that's our duality invariance condition. Now, one could ask, since we were thinking of deformations, let's just first, to get some intuition, think about what happens if we deform one of these duality invariant Lagrangians to leading order. So we add some small deformation lambda times another function of those two real variables S and P to a Lagrangian L. And we assume that the parameter lambda is sort of inert. It does not transform under duality rotations. One could then ask, what is the condition for the new theory defined by L prime to remain duality invariant at first order in lambda? And it's rather straightforward to see that the differential equation comes from sort of expanding the previous one to leading order, and one gets a condition of this form. So if O satisfies this differential equation given L, where L is assumed to be associated with the duality invariant theory, then this theory is also duality invariant at leading order. But it turns out that this condition is exactly the same as the equation that you would get by imposing that the function O itself be a duality invariant function in the sense that I described before. So this is fairly intuitive, that if you deform a duality invariant Lagrangian by a duality invariant function, that the theory remains duality invariant at leading order in the deformation. Okay, so that's, I think, rather satisfying, but one can lift this beyond a leading order deformation, and that's sort of the idea or the intuition behind one of our theorems. So one of the first rather simple results in our paper, which I rather like, is a differential equation form of this statement. So the statement of the theorem is that if one has a family of theories satisfying a differential equation of this form, that the derivative of the Lagrangian with respect to some parameter is some function O lambda, where O lambda is duality invariant in each of the theories. So notice that the duality variation delta depends on lambda, since it's a function of a Lagrangian. But if all of those functions O along this flow are duality invariant, then the solution, this L lambda as a function of lambda, will also be duality invariant at all values of lambda. This is assuming the initial condition is duality invariant. So if one deforms a duality invariant theory by duality invariant functions along a flow, it generates a family of duality invariant functions, or a duality invariant theories of electrodynamics. Okay, so this is the first result. I'm going to omit the proof of this one, but this is kind of satisfying because this is now, in some sense, reduced the question of describing duality preserving deformations, which was the question I motivated. How do we deform a theory in a way that preserves duality invariance? We've reduced that task to the task of enumerating duality invariant functions. Since given any such function, you can define one of these flows, one of these differential equations. So now let's turn to this task, enumerating the duality invariant functions. It turns out that this is also a fairly simple task because within a given theory, any pair of duality invariant functions are dependent on one another. So there's a functional dependence between them. So the precise statement of this is this theorem 2. So given a duality invariant theory with some Lagrangian L, if you have two duality invariant functions f and g, then they will be functionally dependent upon one another. So some function of two variables evaluated on this f and g will vanish. And I'll show you the proof of this in a moment. But this is also very nice, since now once one has found a single non-trivial duality-invariant function, say one built from the stress tensor, then any other duality-invariant function will be related to this by some functional dependence. So it suffices to find one in some sense.
Question. So I probably missed something. So what's the definition of duality-invariant theory? It's the theory which has invariant equations, right?
That's right. Equations of motion are duality.
And what's the definition of duality-invariant function?
Good. A function is one which is itself invariant under the duality rotation.
Okay. So that's what that was. Yeah. Okay. Very good.
Good. Yeah. Good. Okay. So I'll show you the proof of this. So the proof is due to Sergey, who's in the audience, and I had initially constructed a very ugly, complicated proof of this when I first started thinking about this, and a very useful strategy for coming up with an elegant proof is to present an ugly proof to Sergey, because he will come up with a much nicer one that makes the physics much clearer. So let me show you this very nice proof that any pair of duality-invariant functions are somehow dependent. So the proof goes like this. So we recall from the definition that a duality-invariant function, which, let's see, I showed a moment ago that this differential equation for the function O is equivalent to demanding that the function be invariant under duality rotations. So this I'll take as my condition for a duality-invariant function, where O is the function. So that's the condition for here. The function is now f to be duality invariant. And to study this condition, it's useful to introduce a vector field. So we'll introduce a vector field v, which is in the SP plane. So this is in a two-dimensional space where the variables are the two Lorentz scalars, if you like, s and p. We're thinking of these as now coordinates in some auxiliary space. We introduce a vector field which has the components along the s and p directions that are these two combinations of derivatives of the Lagrangian that appear in this duality invariance condition. So this SLP minus PLS and this SLS plus PLP. So those are the components. First, one can show that if the Lagrangian is not a constant, this vector field will always be non-vanishing. So roughly the sketch of that argument is that if the vector field were zero, so both of its components are zero, these two components, these combinations of derivatives of L, both vanish. And by taking combinations of those two equations, you can show that the Lagrangian must be a function of one combination, which is the combination s squared plus p squared. This is the only solution to these two simultaneous differential equations. But the second condition also would imply that this function is now a homogeneous function of degree 0 in this combination, in this variable s squared plus p squared. But the only way to have a homogeneous function of degree 0 in s squared plus p squared is to be a constant. So for any non-constant Lagrangian, this vector field will be non-vanishing. Okay, so that's one vector field V. Now we'll introduce some additional vector fields. So introduce now the vector field F, which is, if you like, it's really df. It's the derivative of f with respect to s. Here the subscript will always be derivative with respect to the argument. So it's derivative of f with respect to s along the s direction and derivative of f with respect to p along the p direction. And this first equation that I showed for the duality invariance is just the statement that the inner product between the vector field v and the vector field f is 0, so that these vectors are orthogonal. So this is our duality invariance condition for the function f. If we have a second duality invariant function g, by the same argument, it must also be orthogonal. Oh, sorry, this. Sorry, these v. Yeah, no, this is good. Sorry, it must satisfy the same orthogonality condition that it's orthogonal to v. So we introduce the vector field g so that this condition can also be interpreted as the orthogonality of the vector field G to this vector field V. So we do the same argument for the two duality-invariant functions f and g, which must both be orthogonal to V. That's the first step. Then one argues that since these are vectors with two components, the S and P components, so these are two-dimensional vector fields on the plane, if one has two vectors f and g associated with the two duality-invariant functions, which are both non-zero and orthogonal to a third vector field V in two dimensions, those vector fields must themselves be parallel. So f and g are related by multiplication by some function h. And therefore, if those two vector fields are parallel, this determinant, since these two rows are proportional to one another, vanishes. But the vanishing of this determinant is equivalent to the functional dependence between these two functions f and g. So there's some function upsilon of f and g which vanishes, some function of two variables upsilon, which when evaluated on f and g equals 0. And that's the proof that f and g are functionally dependent on one another. Okay. It's a very nice sort of simple proof, which I like. And the reason why this is satisfying is that now we can find, if we like, say, one example of a duality-invariant function and argue that any other duality-invariant function O can be expressed as a function of the one that we've constructed. So which one should we choose? Well, a physically motivated example, which is easy to compute, for instance, is the energy momentum tensor. So as we were saying, you can define the Hilbert stress tensor by varying with respect to the metric, and it can be explicitly evaluated for any such Lagrangian depending on S and P. You get some explicit form like this. And you could ask, how do you see that the stress tensor, or as we'll see, as we'll use later, these Lorentz scalars constructed from the stress tensor, how does one see that this is duality invariant? Well, one could either check by direct computation. You can show that the stress tensor satisfies that condition, which I showed for duality invariance, or you can use a somewhat more general argument. It's known that the derivative of the Lagrangian with respect to any duality invariant quantity, like the metric, is itself a duality invariant quantity. So based on general principles, the stress tensor, since it's a variation with respect to the metric, and the metric doesn't change under duality rotations, the stress tensor must be a duality invariant quantity. Okay, so that means that since we'll deform the Lagrangian, of course, only by Lorentz scalars to preserve Lorentz invariance, these two Lorentz scalars built from the stress tensor, which are the trace of t and the trace of t squared, are natural duality invariant quantities to use. And we know that these must satisfy some functional dependence by the previous theorem, but for writing flow equations, it's often convenient to have both of them. So I'll keep both of them, even though that they will be dependent in any duality invariant theory. Okay, that's roughly the pieces I wanted to show in this section. So let me just overview what we showed in this section of the talk. They're pretty simple conclusions. So a family of theories with some Lagrangians that depend on a parameter lambda, we showed that these are self-dual if and only if the derivative with respect to this parameter lambda is some duality invariant function along the flow. So we can parameterize families of duality invariant theories by duality invariant functions. That was the first thing. And then we showed that any pair of duality invariant functions are dependent on each other. And we showed that any Lorentz scalar constructed from the stress tensor, like the trace of t squared or trace of t, is itself a duality invariant function. So combining these three conclusions, it follows that if you have any family of duality invariant theories, since those obey a flow equation of this form, but if O is duality invariant, it's functionally dependent on the stress tensor, we can replace the O by some function of the stress tensor on the right side. So all of these duality invariant families of theories obey a differential equation with a source on the right side that is some function of the stress tensor. And conversely, since the stress tensor is a duality invariant function, you can go in the opposite direction. Given any function, you generate a family of duality invariant theories starting from some initial condition, which is self-dual. Okay, so that's that's the summary of this part. So maybe I should stop again and see if there's comments or questions.
Sorry, so is it morally correct to say, so basically your duality equation, it tells you, say if you know Lagrangian as a function of t, it tells you what it should be as a function of s. So in fact, it's actually a function of, like, morally of one variable. And I mean, not Lagrangian, but your duality-invariant function. And that's why all duality-invariant functions are functionally dependent, because they're morally like function of one argument.
That's right. That's exactly the right intuition, that this duality invariance condition cuts down dependence from two variables to one variable. So everything is secretly a function of one variable. That's right.
So this will work if you have one f-mu tensor, yes? If you have many f-mu tensors, like duality would like work simultaneously on all of them, and this won't work, right? Or this argument.
That's right. So if you have a theory for a collection of field strengths f, well, now it depends on what sort of duality symmetry you want to impose. But if you impose symmetry under duality rotations involving only each individual field strength, then it's a collection of self-dual theories of electrodynamics. So if there's n field strengths, then things can in principle depend on n variables. But one could then ask, well, okay, what if instead of just imposing duality rotations that mix only each field strength fi into the corresponding gi, you could imagine imposing some larger duality invariance that also rotates fi with, say, gj, a different one. That would further cut down the number of independent variables to less than n. But at least for the naive duality, there would be n independent variables. That's right.
Yeah, thank you.
Good. Other questions?
Is there any relation to any consequence of these facts for the way how the Lagrangian actually changes under duality? For example, Lagrangian changes sign. I think Born-Infeld also, I don't remember. So in principle, you can ask what is actually the change of Lagrangian itself. And
that's good. I think my intuition is that no, since we found these results by imposing that the equations of motion don't change under the duality rotation, which would be insensitive to how the Lagrangian changes, since we're looking only at the equations of motion. So naively, my answer would be no, but maybe there's something that I'm missing, and one could extract something about.
It looks like once you take derivatives, for example, you take derivative of the metric, you get stress tensor, which is invariant. So there are certain, maybe one can quantify what's the non-invariance of Lagrangian, and what does it mean for under duality? Assuming invariant.
I think in Maxwell case, infinitesimally it shifts by a topological term, right? So that's why variation with respect to the metric is insensitive to that.
Okay, yes, but it also changes sign. No, it changes sign.
I would say it generically picks up a factor. In the discrete transformation, it changes the sign. Otherwise, it gets a factor like cos alpha squared.
Okay. So there should be still some consequence if you take derivative over some parameter. It somehow you get into this framework of derivatives over the parameter, so which may be more invariant than just Lagrangian itself.
Yes, I think indeed. So I think one would have to do an additional step of analysis, but I could imagine taking a flow equation like this and then taking, say, a variation of both sides. So if you do a duality variation of both sides, like a delta sub alpha or delta sub theta, if you like, then perhaps one could relate the way that the Lagrangian varies, which would indeed be like maybe a topological term or a rescaling or something like that, to a variation of the stress tensor. And maybe one can then commute derivatives, since the stress tensor is itself a metric variation of the Lagrangian, which would give you an equation that relates the term that is generated by the Lagrangian under duality rotation to metric derivatives of that term generated in the Lagrangian. Maybe one can get such a constraint, but it's not immediately clear to me whether it would be useful. That's a good question, though. Okay. Other questions or comments?
Can you do this in general dimensions? And if yes, does it reproduce TT bar somehow?
By doing this, you mean looking at electrodynamics in general dimensions, or
general dimensions? Yeah, I see that this duality doesn't make sense, right?
Right, at least the naive duality doesn't make sense. One could maybe try to generalize this in certain even dimensions to, say, p-form electrodynamics and impose some notion of duality invariance for the p-form theories and look at stress tensor flows for those theories. I think that could be interesting. We've thought about that a little bit, but I don't think there's as much of a literature on that, and I don't have any results on that to report, at least. But that's an interesting direction.
And so there is no way to connect it with TT bar, right? Just similarity.
Well, one might be able to relate it to stress tensor flows, perhaps in the same way. It's not obvious if it would be related to the specific quadratic combination I was showing, which is sort of motivated by TT bar, since I'm not sure which. Sorry, if there's a preferred. The reason why the TT bar appeared there was because we wanted the deformation which generates Born-Infeld specifically. That's where that came from in the 4D case. So I'm not sure what would play the role of Born-Infeld if we were looking for a specific quadratic combination in higher dimensions, but there may still be some generic statement about stress tensor flows, although not specifically a TT bar-like combination.
Mm-hmm. Thank you.
Right. Any other questions? Okay. Well, in my last few minutes, 10 minutes or so, I want to connect this to another presentation, a different way of writing duality-invariant theories of electrodynamics, which connects to the question we had a few minutes ago about this moral picture, or this morally the statement that duality invariance is cutting things down to functions of one variable. So we can actually make this manifest. So that was the intuition that duality invariant electrodynamics is sort of secretly a univariate or one variable problem. So this was the intuition we were discussing before. So one could ask, is there a way to make this reduction to one variable obvious or manifest? And I think some of the early work, although there was also some follow-up, some early work on this by Ivanov and Zupnik showed that there is a way to do this by introducing an auxiliary field. So the way that this formalism works is that you introduce another antisymmetric tensor, much like the field strength, you introduce an auxiliary V, and it's convenient for writing, the Lagrangians will write in a moment, to convert both F and V to spinor indices. So we use these polymatrices, or these Weil matrices of SL2C, to convert both F and V to spinor indices. So we'll have both an F with undotted indices and an F bar with dotted indices, and likewise for V. So we'll have these these versions of the field strengths, and also scalars that come from contracting the dotted or undotted indices. So I'll call the scalars phi and phi bar, that are contractions of the field strength, nu and nu bar, which are contractions of the auxiliary, and one can also take products of V with F, which I'll just write with these dots. This is just a bunch of notation, but the reason why this is convenient is then one can write a fairly general Lagrangian. So what one could do is write this sort of family of Lagrangians, which has one piece depending on the phi's, which remember are contractions of F with F, one piece with contractions of the auxiliary, nu and nu bar, one piece that links the two, so these V dot F are contractions of F with the auxiliary, and then all of the data that describes different theories will go into this interaction function, this E, which I've written it to depend on only the product, the combination nu times nu bar. You could consider a more general function E that depends on nu and nu bar separately, But as it turns out that if you would like this theory to describe a duality-invariant theory of electrodynamics, it suffices to impose that the interaction function E only depend on this real combination, this A, which is nu bar. So the claim is that if you take this Lagrangian and integrate out the auxiliaries for any such function E, depending only on nu times nu bar, you will recover some Lagrangian for, say, S and P, which satisfies the differential equation I showed you before for a duality-invariant theory. So any such function E gives rise to a duality-invariant theory, and in fact, the converse is true. You can find a function E that describes any Lagrangian L, which satisfies the differential equation before. So this is a manifest way of showing that the family of duality-invariant functions is described by a function of one variable, this interaction function E. This is a nice presentation, since if you choose not to integrate out the auxiliaries and just study this theory itself with the V's, the duality rotations acts in a very simple way. It's essentially a linear rotation of the fields that's kind of mixing the F into some combination of F and V with a similar action on all of the barred fields. So this is a nice presentation, or a nice reduction for these duality-invariant theories. Okay, so this is this Ivanov-Zupnik presentation. Now, this will make manifest some of the results about stress tensor flows, because one can also compute the two Lorentz scalars I mentioned before that are built from the stress tensor, the trace of t and the trace of t squared. And one can show that those two scalars are built only out of the interaction function E, its argument A, and the derivative E with respect to A. So both of these combinations only involve E's. And this means that if you deform the Lagrangian I showed on the previous slide, so if I say write a flow equation for a derivative of this Lagrangian with respect to a parameter, which is driven by a function of the stress tensor, any such function on the right side, since it's built from these combinations up here, can be expressed purely in terms of E, A, and its derivative. So any such equation gives rise to a closed differential equation just for the function E. So we can interpret a stress tensor flow as leaving the first several terms in this Lagrangian unchanged, these don't change at all, and only modifying the interaction function. And since changing the interaction function leaves you within this family of duality-invariant theories, this makes it clear that any stress tensor deformation is going to preserve duality invariance, since it keeps you in the family of theories parameterized by the functions E of A, just subject to some, say, differential equation for E. So I think this is very nice. This kind of makes it clear. Let me show you an example of such a flow, just to be a little more concrete. So here is one flow that you could study. This is the so-called root TT bar operator, for reasons you can ask me about afterwards if you like. But this is some funny combination of stress tensor invariants, this trace t squared and trace t. This has mass dimension 4, so it's classically marginal, if you like. You could think of it as a deformation which preserves conformal invariance or scale invariance if you start with a scale invariant C. And we can solve this flow equation explicitly. So if we begin with the initial condition of 0 interaction function, E of A equals 0, which is Maxwell, you get some differential equation from this flow, which looks like this, and one can find the solution. So the solution is some particular interaction function which depends on the square root of this combination A. Remember, A is a combination of the auxiliaries, the nu and nu bar. So this is one flow that you could study. It's natural to ask, what theory does this describe? Is this some interesting theory of electrodynamics? And it turns out that this is exactly this so-called modified Maxwell theory of electrodynamics, which I've written for you now in the conventional notation with all of the F's restored. And this was found some years ago by looking for the most general conformally invariant and duality invariant extension of the Maxwell theory, and finding that there is a unique such extension. So if you impose that a family of theory of electrodynamics be conformally invariant and duality invariant, and reduced to the Maxwell theory in some limit, you find this as the unique theory with those properties. So this is nice. We can describe this flow with auxiliary fields. I should comment that in previous work, it was known that this theory in the usual presentation without auxiliary fields does satisfy this stress tensor flow. So really what I've shown you here is just presenting it in a way with auxiliary fields, which is equivalent. But something which was not known before, this is the last result I'll tell you about, is how to describe a generalization of this theory, a two-parameter family of theories, using auxiliary fields. So this two-parameter generalization, which I'll call L sub mod max Born-Infeld, this depends on two parameters, and this reduces to the mod max theory when one parameter is taken to 0, and it reduces to the Born-Infeld theory we saw before when the other parameter is taken to 0. So it generalizes both of these theories. I'll show you the Lagrangian. It's a bit ugly, but this Lagrangian is really just taking the expression for the Born-Infeld theory, which has a square root of 1 plus alpha squared over 2 f mu nu, and replacing the f mu nu under that square root with this modified Maxwell Lagrangian. That's the replacement we make to get this generalized version. And this two-parameter family of theories, these are all duality-invariant theories of electrodynamics at any value of the two parameters. And this satisfies two commuting stress tensor flow equations. So what I mean is that you can either begin with the Maxwell theory and deform by this root TT bar combination I mentioned to get the modified Maxwell theory, and then use that as an initial condition to perform a TT bar flow to get this two-parameter guy, or go in the opposite direction. You can deform Maxwell by TT bar and then the results by root TT bar, and you get the same answer either way. So there's two stress tensor flows that give this guy. And one could ask, is there a presentation of this two-parameter family of theories in terms of auxiliary fields? So this had not been written down before, but I'll just flash the answer. In order to present this, we used a slightly different auxiliary field formulation than the one that I showed you before. This was also in the original paper by Ivanov and Zupnik, but this is roughly the Legendre transform of the formulation I showed you before. So instead of using this interaction function E of A, in this formulation, we have an interaction function H, which is, again, roughly the complex Legendre transform of E in these two variables, nu and mu. So you can think of this as just a different presentation where instead of E, I use H. In this presentation, H is all of the data you need to describe some duality-invariant theory of electrodynamics, assuming H depends on only the real combination B, which is mu times mu bar. So this is just some different presentation. And what we found is that this two-parameter family, this mod max Born-Infeld family of theories, can be described with an explicit interaction function of this form, which is slightly complicated, but it's not terrible. So this is the result for this mod max Born-Infeld, and all of the same words that I said before apply, that this other formulation makes it manifest that stress tensor deformations leave you within the family of duality-invariant theories because they only modify H, this interaction function. Okay, it was slightly fast because I'm running out of time, but maybe I'll quickly summarize, and then if there's questions, we can run through questions or comments. So to wrap up, let me tell you just, again, the main things that we showed. So we established essentially a one-to-one correspondence, that every duality-invariant family, so every parametrized family of self-dual electrodynamics, obeys a flow equation where the derivative with respect to a parameter is a function of the stress tensor. That's one result. The converse is straightforward, that since the stress tensor is duality invariant, any function of the stress tensor also gives a line or a one parameter family of self-dual electrodynamics theories. We studied these using this auxiliary field formulation due to Ivanov and Zupnik. That makes certain aspects manifest. And we derived this new way of presenting the mod max Born-Infeld theory, this two-parameter family of theories. And a few interesting future directions that I'm curious about. This same PDE that I showed you, the one involving derivatives with respect to S and P, that same differential equation appears in other contexts. So one context is in the study of certain 2D integrable sigma models. The same differential equation appears. So I'd like to ask whether one could also use a similar auxiliary field formulation in that setting for these 2D sigma models. Another question is, can you extend this analysis to explore deformations not of 4-dimensional electrodynamics, but of 6-dimensional theories of chiral tensors, a 2-form with a self-dual 3-form field strength? And there's some work in progress going on now on that direction. And the third direction, which we mentioned briefly in response to a question before, is whether one can use this result, that these theories are generated by stress tensor deformations, to endow them with some geometrical interpretation, like a field-dependent change of coordinates, which has been studied in the 2-dimensional setting. And does such a geometrical interpretation give us any mileage or teach us anything about duality-invariant theories? So I think these are interesting questions. Answering some of these questions could provide new insights into how to explore the space of field theories with these flow equations. So let me stop there. Thank you.
Thank you. Are there any questions?
Can I ask a question? Can you remind us whether a TT-bar deformation like gives you some bonuses in non 2 dimensions, in like 4 dimensions or something? I mean, if this TT-bar connects you to a free theory, for example, can you tell us the spectrum in the finite volume or something like that?
That's a good question. So at the moment, no. These the spectrum is a property that requires you to understand the TT-bar deformation quantum mechanically. So it needs to be, say, defined as a quantum operator by point splitting in order to use the argument of Zamolodchikov in order to get a flow equation for the spectrum. In higher dimensions above 2, it's not yet known how to define some analog of the TT-bar deformation quantum mechanically. And I would even suspect that this sort of naive, purely bosonic combination of stress tensors that I showed maybe way at the beginning, this combination of stress tensors that defines Born-Infeld, this, I think, by itself probably will not be able to be defined quantum mechanically by point splitting. So this, I think, by itself may not give us any mileage, but my hope is that it may be that by imposing some additional structures such as supersymmetry, it might be that the supersymmetric version of the TT-bar deformation, since it has additional constraints, in that setting, maybe one could hope that it could be defined quantum mechanically and one could derive flow equations for theories or quantities in the quantum theory. That's merely speculation, but the short answer to your question is no. In 4 dimensions, we don't get any results about, say, the spectrum from this.
Okay, thank you.
Sorry, what is SNT in the sigma model setup?
Oh, good. Yes. So it's a let's see, where is it? So these, in this case, I guess I can maybe even show you in the paper if you'll give me 1 second to find it, since we have explicit expressions in this paper for what the analogs of S and P are in the sigma model context. They're built out of certain traces of combinations of this left invariant current J, which unfortunately my internet, there we go. So I can show you explicitly. Good. So if this J is this left invariant Maurer-Cartan form for these integrable sigma models, where here G is the fundamental field, there's some group valued field, and this J is the Maurer-Cartan form, the kind of most well-studied example is the principal chiral model, which looks like this. But you can define analogs of these S and P, which are in light cone coordinates built out of traces of products of J. So S, much like S is the usual Maxwell theory in 4 dimensions, here S will be the principal chiral model action, or Lagrangian, and P squared is some other combination of traces of J plus and J minus. And it turns out that the condition for a Lagrangian depending on these two combinations, L of S and P squared, in order to be classically integrable, which means it admits a zero curvature connection, or a zero curvature representation for its equations of motion. So this Lax connection, flatness of this Lax connection will be equivalent to its equations of motion if and only if the Lagrangian satisfies this differential equation, which is exactly the same as the duality invariance condition, which I find somewhat surprising. So there's some connection between the condition for a nonlinear electrodynamics theory to be duality invariant and the condition for some theory of some group valued fields in order to have a zero curvature representation for its equations of motion with this particular Lax. But to answer your question, these are the S&P.
Other questions?
In this concrete, following the question, so this Lax connection that you find, is it like, is there a proof that this is unique? Or, I mean, maybe there are other theories that have different Lax connections? Or if the theory is integrable, then it has to satisfy this condition?
No, I think there's no guarantee of the uniqueness of the Lax connection, because one can, for instance, do sorts of these gauge type transformations that modify the Lax connection in some way, but such that the flatness of the Lax connection is still equivalent to the classical equations of motion. So I don't think there's a guarantee that that this thing is unique in any sense. But this is one particular simple form of the Lax that one can choose, which is rather nice since it reduces to the conventional Lax connection you use for the principal chiral model when the Lagrangian is just this variable S. But indeed, to your question, there may be, there might be a more general family of Lax connections, or it might be that that this condition is somehow missing something, that if one had considered a more general ansatz for the Lax connection, it might be that some other condition appears rather than this one. So this direction hasn't been systematically explored. This is just kind of a hint, I guess. But if at least you restrict to this ansatz for the Lax, then it appears that the same duality invariance condition comes out rather naturally.
Okay, thanks. One more comment that so this equation that is equivalent to the Courant Hilbert one that is solved ago. So the equation is known to admit space of solutions parameterized by one function of one real variable, right?
Yes, that's
so
right.
It's not extremely surprising that one gets a theory or family of theories that should be parameterized by a function of one variable. And another thing is that, can we say that the TT bar-like flows also, in a sense, become a inevitable option, because since the T mu is invariant, we have a stress tensor that is invariant, so we build a Lorentz invariant structure from it, T squared, and whatever it is, since it is duality invariant, it should be connected to any other duality invariant, because it should be, there is only one invariant, and any function of it would be as good as any other. So, I mean, naively, this seems to suggest that since the invariant is only one, since there is only a function of one real variable, and the T mu is invariant, then it trivially follows that any T-dependent deformation would satisfy this condition that you are looking for. Is that correct?
Yes, that's right. So for the first comment, for those that aren't familiar, let me just show quickly the Courant-Hilbert equation that we were referring to. So if one does a change of variables to these P and Q, then this condition for duality invariance that I wrote down becomes very simple. It's just the product of L, the derivatives of L with respect to P and Q must be equal to 1. And indeed, this is known to have a family of solutions that's parameterized by one function, say V, which one can write in this way. So indeed, it's not surprising that the solution space for these duality invariant electrodynamics theories should reduce to a function of one variable, but I think the Ivanov-Zupnik formalism does this in a very nice way. It makes it sort of physically transparent. When it presents this reduction to one variable in a way that's useful for computations. That's the first comment. To your second comment, I agree that in some sense, it's not at all important that we are using flows built from the stress tensor. I motivated the talk by saying that it seems very interesting that this Lagrangian satisfies a flow equation built from the stress tensor, but in reality, one might say that nothing is special about the stress tensor in this setting, because if you had any other duality-invariant function, you could have written some analogous flow equation like this, which maybe takes some more complicated form, but it's guaranteed that there exists some function of whatever invariant you write down that drives this flow. That's certainly true. The reason that I prefer the presentation in terms of the stress tensor is that among the family of all duality-invariant functions that you could write down, the stress tensor seems especially natural in the sense that it's physically motivated, it's easy to compute by taking functional derivatives with respect to the metric, and for these other reasons that one might hope that perhaps with some modification like supersymmetry, that stress tensor deformations might give you some additional computational control. So for instance, flow equations for other observables might be easier to cast in terms of stress tensor deformations, even though I agree that in principle you could use any duality invariant function you like.
So one last comment is in principle this SO2 symmetry can also can be made manifest for the Lagrangian. So does this give any advantage to have a manifest symmetry in the Lagrangian for this duality symmetry?
You're asking, does the auxiliary field formulation that makes it manifest have any advantages? Like this sentence?
No, I mean, this is still not what I had in mind. I mean, having both electric and magnetic potentials in the Lagrangian manifest. So
using a doubled formalism where you have both fields and they rotate.
Would that give any advantage?
That is a good question. Let's see. I could imagine perhaps, since even in this presentation, this non-doubled formalism where the duality rotation acts rather simply, it's still the case that the kind of first non-interaction terms in this Lagrangian, these are still not invariant under this duality transformation. It's still true, as it was in the Maxwell case, that these terms, they transform under duality rotations, but the equations of motion are still invariant. So it may be that introducing a doubled formalism where the Lagrangian is invariant or where you rotate between a doubled pair of fields might allow you to more naturally address some of the other questions that we've heard, like Arkadi's question about can one probe the term that's varying in the Lagrangian or something like this. But it's not immediately clear to me what benefit there would be. I could imagine there could be some, but I don't know what it is.
I'm sorry, and you say here any such Lagrangian gives rise to a self-dual theory of electrodynamics, and the converse is also true?
Yes, so this given any Lagrangian which solves that differential equation, one can construct a function E such that this theory is equivalent to the one you started with. That's right. So this is an if and only if.
Okay.
So one last question. So for the Born-Infeld, the equation, the function E is not known, or it's just complicated?
For Born-Infeld, the function E is known, but it's rather ugly to write down. The function E there is algebraic, but it's a root of a quartic equation, if I remember correctly. So it's fairly ugly, but one can still characterize it.
Thank you.
Okay, it seems that we don't have any other questions. So thank you very much for a nice talk.
Great. Thank you for the questions.
Thank you.
Thank you everyone for coming, and hope to see you next time.